As we know, COVID-19 that emerged since early January 2020 is responsible for the current pandemic and the source of the predicament we now live in. Currently, there is no specific antiviral treatment for COVID-19. The most common symptoms for COVID-19 is fever, sore throat, dry cough, and tiredness. We choose aspirin for our integrated project as it can help treat some of the symptoms to fight against COVID-19. Assalamualaikum and salam sejahtera abid to the lecturers and my friends. We are from Group 27. We'll present our integrated project for this semester, which title is The Production of Aspirin. My name is Fatihah, and my group members, which are Izzati, Nabila, and Zul.
Introduction. Aspirin is a type of drug in the family of salicylates where salicylate have been derived from the willow tree bark. Aspirin acted as medicine to reduce symptoms of COVID-19. Aspirin prepared by chemical synthesis from salicylic acid through acetylation with acetate anhydride in the presence of sulfuric acid as a catalyst. It is odorless, colorless to white crystal or crystalline powder and miscible with water, and aspirin has both anti-inflammatory and antipyretic effect. The usage of the aspirin is used to reduce swelling in conditions such as arthritis and used to relieve pain, fever, and inflammation associated with many conditions including the flu.
Next is economy issue. Future marketing potential. Based on the forecast about the market trend for aspirin, the global market is estimated to augment at a compound annual growth rate CAGR of 2.53%, increasing from $1.979 billion in 2019 to $2.299 billion by the end of 2025. There's some facts that the forecast to be true in future, which are pandemic of coronavirus, yet vaccine still not found. The second is aspirin can reduce cold and fever, which are the symptoms for the coronavirus disease. Besides that, migraine is known can affect more than 10% of the population. Hence, such event will contribute to the market growth of aspirin, and the sale of aspirin will increase. Next, I will move to the price of aspirin. The price of a certain product depends on the demand of that product. In hypothesis, the price increases gradually with the demand. Based on the bar charts besides, Japan has the highest price for aspirin. This is because it has the highest demand as population of people in Japan is the highest.
In economy issues part, the global aspirin market demand is estimated to augment at a CAGR of 2.53%, increasing from 19.79 million tons in 2019 to reach 22.99 million tons by the end of 2025. Due to the high demand of aspirin in the global market, there is also an increase in the number of producers. According to the chemical business, the supply market of aspirin in 2017 was 6.1 million tons and was estimated to be 7.95 million tons in 2035 with a CAGR of 4%. Based on the line graph from this figure, we can conclude that the supply and demand for aspirin has gradually gone up from year 2019 to 2025. The plant capacity of aspirin. We have calculated the difference between demand and supply to estimate the plant capacity to be produced in 2025. The global deficient for aspirin is 15.04 million tons per year. In this project, the working hours for a year are 350 days and it operates continuously for 24 hours each day and assuming 50 days as a maintenance day in the whole year. We will take about 4% of the global shortage, which is 60.16 million tons. Hence, the production rate is estimated to be 72 kilotons per hour.
Environmental and safety issue. For production of aspirin, there has a three-way treatment, which is acetic acid, salicylic acid, and wastewater. For acetic acid absorption, ion exchange, evaporation, precipitation, and membrane technique are the treatment to remove waste acetic acid. For salicylic acid, the material and its container of waste salicylic acid must be disposed of as hazardous waste and for wastewater, sewage treatment is one of the ways to impurities from wastewater before they reach natural bodies of water. Precaution of handling matter and storage for aspirin is moderately toxic by ingestion. Avoid breathing dust of fume or gas or mist or vapor and spray. Also need to avoid prolonged or repeated exposure. And lastly, keep the container tightly closed. Store in accordance with information listed on the product insert.
In process description, aspirin, or also known as acetylsalicylic acid, is commercially prepared by chemical synthesis from salicylic acid through acetylation with acetic anhydride. Salicylic acid and acetic anhydride with an assumption ratio of 1:3 is pumped into a mixture at 25 degrees Celsius. Then the mixture is heated to 92 degrees Celsius before entering PBR reactor to react the salicylic acid and acetic anhydride with the presence of sulfuric acid as a catalyst for a period of time sufficient to cause the acetylation of the salicylic acid to proceed to substantial completion with the formation of acetylsalicylic acid and acetic acid. The conversion of salicylic acid in the reactor is 75%. The reaction mixture is then transferred to a distillation column to separate between salicylic acid and the other three components, acetic acid, acetic anhydride, and acetylsalicylic acid, according to their respective boiling points. Salicylic acid will 100% come out from the bottom feed and treat as a waste, while the top feed will produce acetic acid, acetic anhydride, and acetylsalicylic acid. 100% efficiency of distillation column is assumed. The top feed is then cooled to a terminal temperature of 25 degrees Celsius before being fed to a crystallizer whereby a major portion of the acetylsalicylic acid formed in reactor precipitates out and is separated from other liquid by filtration. The end product was then washed by water and then dried out to obtain the desired crystallized form of end product. The mother liquid from the filtration comprising of free acetic acid formed during the acetylation step and acetic anhydride is pumped through a LLE extraction to separate acetic acid and acetic anhydride based on their miscibility with water. Acetic acid, which is miscible in water, will be extracted out and treated as a waste, while acetic anhydride with partial solubility in water will be at the raffinate stream that acts as a recycle stream. The process flow diagram of the production of aspirin is shown in this page.
Material and energy balance. I choose paper reactor as the example for this part. For material balance, with the conversion of salicylic acid at 75%, the reaction will change the inert 100 kmol per hour salicylic acid to 25 kmol per hour salicylic acid. The reaction in the reactor will produce two products, which are aspirin and acetic acid. Aspirin is the main product, while acetic acid is the byproduct. Both of them are 75 kmol per hour because the reaction is equimolar. For energy balance, enthalpy feed for the reactor is 1251.525 kJ per kilomole, while the enthalpy product is 561.50 kJ per kilomole. After we calculate the Q, we got negative 1416149.75 kJ per hour. The negative sign indicates the reaction is exothermic reaction.
For chemical reaction part, we choose the most suitable process from materials, catalyst, and reactor for our project. For process, we choose method of synthesis of salicylic acid through acetylation with acetic anhydride using a strong catalyst. As for the raw materials, we choose salicylic acid and acetic anhydride. We also choose sulfuric acid as our catalyst because sulfuric acid is a strong acid that can speed up the reaction. We also choose the PBR reactor as our main reactor. Next, in this chapter, we derive the feed rate to reactor, change within reactor, effluent rate from reactor, and concentration. Also, the rate law for this reaction has been determined.
Separation process. I choose dissolution column to design in this part. DC will separate the LK at top and the HK is at the bottom product. Our DC, the alkane is aspirin, while the HK is salicylic acid because the boiling point of salicylic acid is the highest. At the condenser, we calculate the head duty and we get the value is 1867.7 kJ per hour. To find the number of stages, shortcut method has been used. Firstly, by using Fenske equation, we can find the minimum number of stages. The value after the calculation is 15.003. Next, from first Underwood equation, the Q value of saturated liquid equals to 1. This can help us to find the theta value which is needed to find the Rmin. Lastly, by using this formula, we get Rmin equals to 1.0384. With the ratio 1 to 2, the actual reflux is 2.0768. By using Gilliland correlation equation, we can find the actual number of stages. The actual number of stages is 15.25. The tray efficiency is 98.38%. We calculate by n min over n times with 100. After that, we calculate the diameter of the tray by using this formula. The diameter is 1 meter. The last one, we find the height of the column. We use this formula and get the height is 11 meter.
For computer-aided plan design part, in this chapter, SuperPro Designer software have been used to find the mass flow rate of our components for the production of aspirin and to compare the calculation with the mass balance that have been calculated manually. For unit operation PBR reactor, the material balance for reactor is tested by using SuperPro simulation. The conversion of reactor is estimated to be 75%. Percentage error for the comparison between manual calculation and SuperPro simulation is 12.5% for acetic anhydride, 35% for aspirin, and 35% for acetic acid. For unit operation distillation column, the material balance for distillation column is also tested by using SuperPro design simulation. In top fit, which is stream 12, the percentage error for acetic acid, acetic anhydride, aspirin, and salicylic acid is 105.8%, 59.7%, 2.9%, and 513.9% respectively. While the bottom fit percentage error, which is stream 29, for acetic acid, acetic anhydride, aspirin, and salicylic acid is 30.1%, 86.3%, 352%, and 765.8% respectively.
Computational chemical engineering. For mass balance, first we enter the input mass flow rate of salicylic acid, which is 13,812.1 kg per hour, then divided with the molecular weight to get the molar flow rate, which is 100 kmol per hour of salicylic acid. Then we enter the input mass flow rate of acetic anhydride, which is 30,627.0 kg per hour, then divided with the molecular weight to get the molar flow rate of acetic anhydride, which is 300 kmol per hour. And finally, we get balance for both output and input, which is 400 kg per hour for input and 44,439.03 kg per hour for output. And also, the manual calculation for mass balance in reactor R101 is similar with MATLAB output. For energy balance, firstly we enter the input temperature, which is temperature 1 is 298.15 Kelvin and temperature 2 is 365.15 Kelvin. Then we enter the output temperature, which is temperature 2 365.15 Kelvin and temperature 3 is 433.15 Kelvin. And finally, MATLAB output for energy balance in reactor R101 also shown the similar answer with the manual calculation. For error handling, the error will display if enter invalid flow rate input or negative value. Thus the value of input and output for mass balance are not balanced. So we need to input again with the positive value. Next, for numerical method. Equation that we are used are from reactor R101. In this case, we want to find the roots. The most suitable method that we are choose is Newton-Raphson, because Newton-Raphson only gets one value, but we need to derive the equation above. From the graph above, The value of roots is in between negative 0.2 to negative 0.1 and 0.120. The first guess that we attack is negative 0.115 because it is in between negative 0.2 to negative 0.1. And finally, the real roots obtained using Newton Raphson method is negative 0.10415.
Conclusion. The proposed plant is expected to produce 4% deficiency of aspirin, have plant capacity of 72,000 kg per hour in future. According to the material balance calculation, pepper writer produced 13,511.85 kg per hour of aspirin. From the calculation of energy balance, the heat release is negative 1416149.75 kJ per hour. The design of the design column is 11 meter height, 1 meter diameter, and 15.25 stages with 98.38% rate efficiency. The kinetic rate expression is derived also, and circumventory table is constructed in this report. After using SuperPro to calculate material balance, there is 25% error for aspirin at outlet of the reactor compared to the manual calculation. The final value from MATLAB program is the same with the manual calculation for chapter from material balance.